Hello everyone, in this video we will be solving paper 2 variant 1 October-November 2023 AS level chemistry, starting with question number 1. The elements phosphorus, sulfur and chlorine are in period 3 of the periodic table. Table 1.1 shows some properties of the elements phosphorus to chlorine. The first ionization energy of sulfur is not shown. A part 1 asks you to complete table to show the number of electrons in a 3p subshell and the total number of unpaired electrons in an atom of phosphorus, sulfur and chlorine. Just to give you a brief summary, subshells, so each energy level or each shell, so shell 1, 2 and 3 are divided into subshells, each of which can contain orbitals. So the first subshell is the S subshell, the second one is the P subshell, which contains p orbitals. The subshell S contains only one orbital, so that's 1s, 2s and then 2p. Subshell P has 3 orbitals. Now each orbital can carry up to 2 electrons, and when you have 2 electrons in a single subshell in an orbital, they are found in opposite spin as electrons repel each other. So let's start with phosphorus and write down its electronic configuration to find the number of electrons in its 3p subshell. Phosphorus has an atomic number 15, so you have 1s2, 2s2, 2p6, that's 10 electrons, and then 3s2, 3p3. What that means is you have the 1s orbital, so you have an orbital in the first orbit, and then you have the 2s orbital. 1s orbital is occupied by 2 electrons, the 2s orbital is also occupied by 2 electrons, and then you have the 2p orbitals. So you have 3 orbitals and they are occupied by 6 electrons. These are 2px, 2py and 2pz orbitals. Then you have the 3s orbital, which is also occupied by 2 electrons, and then you have 3p orbital or 3p orbitals, and each of them is filled by 1 electron. As I mentioned earlier, if electrons always prefer to occupy an empty orbital, and when all of them are occupied by 1 orbital, by 1 electron, then electrons start pairing up. So when it comes to sulfur, it has the atomic number its atomic number is 16, so it has 16 electrons. So it will have the same electronic configuration as phosphorus, except in the 3p orbital it will have 4 electrons. So its electronic configuration would be 1s2, 2s2, 2p6, 3s2 and 3p4. Now this 4th electron will pair up with one of the electrons in a 3p orbital. And then same goes for chlorine. Chlorine has 17 electrons, so instead of 3p4, its electronic configuration would be 1s2, 2s2, 2p6, 3s2 and 3p5. So this 5th electron pairs up with the 2nd electron in the 3p orbitals. Now looking at this, you can answer the number of 3p electrons in each of these elements. For phosphorus, that would be 3. For sulfur, this would be 4, and for chlorine, that is 5. As for the number of unpaired electrons, in phosphorus, all of the electrons in the 3p subshell are unpaired, so you have 3 unpaired electrons. In sulfur, you have 2 unpaired electrons, and in chlorine, there is only 1 which is not paired up. Part 2. Construct an equation to represent the first ionization energy of phosphorus. Ionization energy is the energy required to remove an electron from 1 mole of gaseous atoms. So you have 1 mole of gaseous phosphorus atoms, and when you remove an electron, that forms 1 mole of gaseous phosphorus ions, 1 mole of positive ions in addition to an electron. Part 3. 3 possible values for the first ionization energy of sulfur are given. Circle the correct value. Explain your choice by comparing your chosen value to those of phosphorus and chlorine. So you're given with ionization energies of phosphorus, first ionization energy. Okay, that's too thick. Here you have the first ionization energy of phosphorus and that of chlorine. So what that means is, when you want to remove this first electron from a phosphorus atom, you will need 1060 kilojoule per moles of energy. And when you want to remove an electron from a 3p orbital, from here, you will need 1260 kilojoule per moles of energy. Now they want you to predict how much energy will be required to remove this electron from the 3p subshell, or the last subshell in a sulfur atom. Generally speaking, the ionization energy increases across the period. So you go from phosphorus in group 5 to sulfur in group 6 to chlorine in group 7. Across the period, ionization energy should increase. And this happens because the number of protons in the nucleus increases. So from 15 to 16 to 17 protons in the nucleus. This will increase the nuclear attraction, as protons have a positive charge. So the nuclear attraction for outermost electrons will increase, and this will, as the number of shells across the period remains the same, shielding effect will also remain the same. So in short, you have greater nuclear charge and therefore greater nuclear attraction for the outermost electrons. What that means is, you will require a higher amount of energy as you go across the period to remove electrons, because the attraction between outer shell electrons and the nucleus will have increased. So chlorine has a greater ionization energy than sulfur, which means the ionization energy of sulfur must be less than 1260. So it cannot be 1320. And if you were to follow the trend, sulfur would have a higher ionization energy than phosphorus. However, that's not the case. Sulfur in fact has a lower ionization energy than phosphorus, because the first electron that's removed from sulfur is removed from a pair of electrons in 3p orbital. So this one over here is the, as I circled, this is the first electron that you remove from sulfur, and it's paired up with another electron. There is a repulsion between two electrons in the same orbital, which will reduce the energy that's required to remove this electron. However, when you remove the first electron from a 3p orbital in phosphorus, it's not paired up, so it won't have the same spin pair repulsion, which is why phosphorus has a higher ionization energy than sulfur. So the ionization energy of sulfur must be less than 1060, which is why it's going to be 1000 kilojoule per mole. B. Phosphide, sulfide and chloride ions have the same number of electrons. So phosphorus goes from 15 electrons to 18 electrons, which is a gain in 3 electrons. Sulfur goes from 16 to 18. Chlorine goes from 17 to 18. chlorine gains 1 electron, sulfur gains 2 electrons, and phosphorus gains 3 electrons. Part 1 give the full electronic configuration of phosphide ions. That would be 1s2, 2s2, 2p6, that's 10 electrons, 3s2 and 3p6, which is now 18 electrons. Part 2 state the trend in ionic radius shown by phosphide, sulfide and chloride ions. Explain your answer. All of these ions are isoelectronic, which means they have the same number of electrons. However, the number of protons in the nucleus increases from phosphorus to chlorine, or from phosphide ion to chloride ion, from 15 to 17. From 15 in phosphide ion to 16 in sulfide ion to 17 in chloride ion. This increase in the number of protons in the nucleus, or the increase in nuclear charge, increases the nuclear attraction for outermost electrons in the outer shell. As the number of shell again remains the same across a period, the shielding effect also remains fairly constant, which is why the ionic radius decreases from phosphide ion to chloride ions. Okay, let me try to explain using this example. Here you have a phosphorus atom which has 15 protons in the nucleus, and the third shell is the last shell, since these are elements from the third period. And when you compare this to chlorine atom, which has 17 protons and the same distance for the outermost electrons, which is the third shell, due to the greater number of protons in the nucleus, the attraction for outermost shell electrons will be stronger, which will reduce this distance between outermost shell and the nucleus. Hence, the radius of not only atoms but also the ions will decrease across the period. Part C, a student does 3 tests on separate samples of aqueous sodium chloride. Complete table 1.2 with the observations the student makes in each test. So the first test is an addition of a few drops of aqueous bromine. You have chlorine, which is a halogen, and this would have been a displacement reaction with another halogen, except bromine is less reactive than chlorine, or bromine is a weaker oxidizing agent than chlorine, which is why it cannot displace chloride ion from sodium chloride. So you will observe no reaction. Test 2 is an addition of a few drops of concentrated sulfuric acid. So we learned the reaction of sodium chloride, sodium bromide and sodium iodide with sulfuric acid. Sulfuric acid acts as an oxidizing agent as well, so it competes with the oxidizing strength of the halide ion. Chlorine or chloride ion is too strong for sulfuric acid to be able to completely displace it, which is why you don't see a visible reaction. However, if this reaction were to occur with sodium bromide or sodium iodide, sulfuric acid would be able to oxidize these halides to form different products. Test 3 is the addition of a few drops of dilute silver nitrate to sodium chloride. Well, dilute silver nitrate produces precipitates with chloride, bromide and iodide ions in the colors white, cream and yellow respectively. So you would observe a white precipitate of silver chloride in this case. Okay, for reaction 2, here is a comparison of the difference between reactions that happen between sulfuric acid and different sodium halides. With sodium chloride, sulfuric acid is not able to completely oxidize chloride ions. So as you can see, the product includes hydrogen chloride. It's formed in gaseous form, so you don't see a precipitate forming. However, when sulfuric acid reacts with sodium bromide and sodium iodide, it's able to oxidize these halide ions to bromine and iodine respectively, because when you go down group 7, the strength as reducing agent of the halide ions increases. So chlorine is not strong enough to reduce sulfuric acid. However, bromine is a stronger reducing agent, and iodide ion is even stronger than bromide ion. D. Phosphoryl chloride shows similar chemical properties to phosphorus pentachloride. Phosphoryl chloride has a melting point of 1 degree Celsius and a boiling point of 106 degrees Celsius. It reacts vigorously with water, forming misty fumes and an acidic solution. Explain how the information in D suggests the structure and bonding of phosphoryl chloride is simple covalent. Okay, so all covalent compounds react with water to undergo hydrolysis reaction. Phosphoryl chloride would have phosphorus pentachloride reacts with water, for example, to form phosphoric acid as well as hydrochloric acid. So the fact that it reacts with water by hydrolysis to form an acidic solution indicates that it is a covalent compound. As for the simple part, the simple covalent compounds have a structure which involves weaker intermolecular forces as opposed to a giant covalent structure, which, for example, diamond or silicon oxide has stronger intermolecular forces. So in case of simple covalent compound, you would have weaker intermolecular forces or van der Waals forces that act as the primary intermolecular forces, and that's indicated by the fact that it has a relatively lower melting and boiling point compared to those of silicon oxide or diamond, which have much higher melting and boiling point due to their stronger intermolecular forces. So in silicon oxide and diamond, the intermolecular forces are covalent bonds which are very strong, as opposed to the van der Waals forces found in a simple covalent structure. Part 2. Construct an equation for the reaction of phosphoryl chloride with water. As I mentioned earlier, phosphorus pentachloride reacts with water to form these two acids, and we'll use the fact that it's a similar compound to predict that this would also form phosphoric acid as well as hydrochloric acid. Now we just need to balance this reaction. You have 3 chlorine atoms here, so that will be 3 hydrochloric acid molecules produced, and then you have 6 hydrogen atoms on the product side, which means 3 water molecules on the reactant side, and that balances all of the atoms on both sides of the reaction. Part 3, phosphoryl chloride contains a double covalent bond between phosphorus and oxygen. Okay, so phosphorus is in group 5, so it has 5 electrons in the outermost shell. Oxygen is in group 6, so it has 6 electrons in the outermost shell. The double covalent bond between phosphorus and oxygen means that both of them will contribute 2 electrons to the bond in the to the bond overlap. So let's say we denote the chlorine and oxygen electrons by a dot and phosphorus electrons by a cross. So phosphorus will donate 2 electrons and oxygen will also contribute 2 electrons to the double bond, as each single covalent bond requires 1 electron from each element. So 2 or a double bond will require 2 electrons from each participating element. Right, so oxygen has 6 electrons in its outermost shell, 2 of which are used in the covalent bond. Then you are left with 4 electrons in the outer shell, which pair up, which are found as pairs in the remaining shell. Then you have phosphorus, which has used up 2 of its 5 electrons in the outer shell, and 3 of the remaining electrons are found involved in single bonds with each of the 3 chlorine atoms. Now this is a covalent bond, which means the chlorine atoms would also contribute a single electron to this single bond. Then each chlorine atom has 7 electrons in its outermost shell, one of which is used in the bond overlap. So you will find 6 electrons in 3 pairs in all of the chlorine atoms in phosphoryl chloride molecule. Part E, phosphoryl chloride forms when phosphorus trichloride reacts with oxygen. Table 1.3 gives some relevant data. Part 1 asks you to define enthalpy change of formation. This is the enthalpy change or the energy change which occurs when 1 mole of a compound is formed from its constituent elements in the standard states. If they had asked for standard enthalpy change, then you would have added the part under standard conditions. Standard states are the states of solid, liquid or gases that are found at room temperature at regular conditions of temperature and pressure. Part 2, calculate the bond energy of the phosphorus oxygen double bond in the phosphoryl chloride molecule using the data in table 1.3, and you're supposed to show your working. Now this question will be solved in 2 parts. First, you will use the Hess cycle to find enthalpy change of reaction for this reaction. Then you will use this value to find the actual bond energy value of phosphorus oxygen double bond. The reason we do this is to find the phosphorus oxygen double bond energy. You will need the enthalpy change value, which we do not have for now, so you will utilize the Hess cycle. As always, to draw the Hess cycle, you will have 3 boxes, one for the reactants, one for the products, and one for the elements used to make the reactants and products. According to Hess's law, the energy change between going from the elements directly to the products is the same as the energy change when you go from the elements to the reactants and then reactants to the products. What that means is energy change in first step is equal to the sum of energy changes between the second step and the third step. So the table provides us the enthalpy change of formation of phosphoryl chloride, which is negative 592. Since we have 2 of these forming in the reaction, we'll multiply that by 2. Now the energy change for the second reaction, which is formation of 2 molecules of phosphorus trichloride, is negative 289 multiplied by 2, since we have 2 molecules. And in Hess cycle, we don't consider elements like oxygen. It's not a compound, so we do not consider that. And we are supposed to use this cycle to find out the enthalpy change of reaction, denoted by reaction 3. So 2 into negative 592 is equal to 2 into negative 289 plus enthalpy change of reaction, which comes out to negative 606 kilojoule per mole. You'll also notice whenever a question requires you to find out the bond energies of either the reactant or the product, you are almost always given the enthalpy change of reaction for that particular reaction. And if you are not given that, you will need to find it, which is why we used the Hess cycle here. Okay, now you'll use the bond energies to find out the bond energy of phosphorus oxide. In phosphorus trichloride, you have 3 single bonds between phosphorus and chlorine, and in this reaction you start with 2 of these molecules, and then you have the double bond between oxygen atoms. You will break these bonds to form the new bonds between phosphorus and 3 chlorine atoms, as well as the double bond between phosphorus and oxygen atom in the product. Okay, again you have 2 molecules on the product side. Whenever you are calculating bond energies, remember, on the reactant side you break bonds. Breaking bonds is endothermic, so you denote that by a positive sign, and on the reactant side you are making bonds, which is exothermic, so you denote that those energy changes of the bond energies by a negative sign. According to this equation, you will break down 6 phosphorus chlorine bonds, because you have 2 molecules, each of which have 3 single phosphorus chlorine bonds. And also you will break 1 oxygen double bond. Both of these you will be denoting with a positive sign, as bond breaking is an endothermic process. Then you will make 6 of phosphorus chlorine single bonds, because you have 3 bonds in 2 molecules, so you denote that by negative 6 phosphorus chlorine bonds, as well as 2 phosphorus oxygen double bonds, as you have 2 molecules and each one of them will have a bond, a phosphorus oxygen double bond. So again this is making bonds, which will be denoted by a negative sign, and the sum of these energies will be the enthalpy change of reaction that we calculated earlier, right? So as you can see, you make 6 you break 6 of phosphorus chlorine bonds, and then you make 6 of those. The plus and negative cancels out. Now you're left with the bond energy of oxygen double bond. From that you will subtract the bond energy of 2 phosphorus oxygen double bond, and this is equal to negative 606. The table provides you with the bond energy value of oxygen double bond, which is, so the table tells you to break oxygen molecule into 2 oxygen atoms, you will need 496 kilojoule per moles of energy. In other words, this is the energy required to break the oxygen double bond to result in 2 oxygen atoms. So this is equal to, so this bond energy is equal to plus 496 minus the bond energy that we want to find out is equal to negative 606. So the 2 times the energy of phosphorus oxygen double bond is equal to 496 plus 606. That means the energy of one double bond between phosphorus and oxygen atom is equal to 551 kilojoule per mole. Question 2. Barium hydroxide is a strong base which is used in inorganic and organic reactions. Part 1 asks you to state the variation in solubilities of group 2 hydroxides. Solubility of group 2 hydroxides increases down the group. So what that means is, when you go down the group from magnesium to calcium, the solubility of their hydroxides increases. Part 2, state what's observed in reaction 1. So reaction 1, solid barium oxide turns to aqueous barium hydroxide, and because of this you'd observe that a white solid barium hydroxide disappears or dissolves. Most of group 2 precipitates are white in color, so it's helpful to keep that in mind. This question is mainly based on memorization based knowledge. Part 3, suggest a reactant for reaction 2. In reaction 2, you start with aqueous barium hydroxide and end with a solid barium carbonate. Okay, let me just mention here that we saw earlier how the solubility of hydroxides increases down the group in group 2. On the other hand, the solubility of group 2 sulfates and carbonates decreases down the group. What that means is barium carbonate will be most insoluble compared to all other carbonates in group 2. So again you'd see a precipitate forming here, and for this reaction the reactant you'd need is carbon dioxide. Again, this is memorization based. Identify A, which is one of the two products between when the reaction occurs between barium hydroxide, which is a base, and an organic acid, ethanoic acid. So when a base and an acid react, they form a salt and water. So here you have barium and ethanoate ions which combine to form barium ethanoate as well as water. Now the reason you have 2 ethanoate ions in each unit of the salt is because barium, being a group 2 ion, has a charge of +2, and to balance this charge you will need a charge of -2. Each ethanoate ion has a charge of -1, so you will need 2 of these in a formula unit of barium ethanoate. 5. Barium hydroxide is made by the reaction of barium with water. Write an equation for this reaction. Again, this is an equation you are supposed to memorize. So you have barium which reacts with water to form barium hydroxide as well as hydrogen gas. And here you will need 2 water molecules for this reaction to be balanced. B. The mineral barytocalcite. Barytocalcite contains both barium carbonate and calcium carbonate. Both compounds decompose on heating. Part 1. State which compound decomposes first when barytocalcite is heated. Explain your answer. The thermal stability of group 2 carbonates increases down the group. So as you go down the group from calcium to barium or calcium carbonate to barium carbonate, the thermal stability increases. Barytocalcite, a combination of barium and calcium carbonate would decompose first as it has a lower thermal stability, so it's more likely to decompose at a certain temperature. Part 2. Construct an equation for the complete thermal decomposition of barytocalcite. The formula is given. Let me start by the equations for thermal decomposition of barium and calcium carbonate. So you have barium oxide and carbon dioxide for the products here, and then you have calcium carbonate which also forms calcium oxide and carbon dioxide. When you decompose a reactant which contains both of these compounds, then you will end up with both of these products. So you will have barium oxide, calcium oxide as well as carbon dioxide molecule. So you have 2 carbons, which means you will end up with 2 carbon dioxide molecules as well, and the remaining atoms are balanced. You have 6 oxygen atoms, 4 here and the remaining 2. C. Barium hydroxide is used to hydrolyze organic compounds. Figure 2.2 shows the reaction of B with barium hydroxide followed by acidification. Draw the structures of the organic products of the process shown in figure 2.2. Okay, barium hydroxide is used for hydrolysis. Now let's start by identifying the 2 functional groups in B. Those are cyanide or nitrile over here and also an ester. Both of these will be hydrolyzed by barium hydroxide in this case. So the cyanide part will be hydrolyzed to carboxylic acid and the ester part will be hydrolyzed to an acid as well as the parent alcohol. So you can see here the alcohol part has a single carbon atom, which means the parent alcohol had to be methanol. Okay, so you end up with an organic product which contains 2 acid groups, one due to the hydrolysis of cyanide and the other due to hydrolysis of the ester, and then you also end up with an alcohol from the ester. Question 3. Potassium chlorate is widely used as an oxidizing agent and to make oxygen gas. Define oxidizing agent. This is a substance that oxidizes another substance and gets reduced itself. The reason I say substance is because the oxidizing agent can be in the form of an element, an ion or a compound. So for example, when sodium bromide reacts with chlorine, chlorine will act as the oxidizing agent. It will oxidize the bromide ion which has a charge of -1 to form bromine molecule which has a charge of 0. So it's oxidized, as well as 2 sodium chloride molecules. So oxidizing agent itself gets reduced from an oxidation state of 0 to -1. Another example is the redox reaction between iron and copper sulfate, which has a blue solution. According to this reaction, copper ions act as the oxidizing agent. They'll displace, so iron will displace copper in the salt solution. Copper ions will oxidize iron and get reduced themselves by gaining electrons. B. Potassium chloride decomposes unheated. Manganese oxide catalyzes the exothermic decomposition reaction. Complete and label the diagram in figure 3.1 to show the effect of the catalyst on decomposition of potassium chloride. So, an exothermic reaction means that heat energy is released and energy of the reactants is greater than energy of products, which you can see in this energy profile diagram. Here you will need to draw two sketches, one without the manganese oxide catalyst and the other one with the effect of manganese oxide. So, catalysts reduce activation energy. Let's start by drawing the sketch of the profile without the catalyst. Okay, so the difference in energy from the reactants up until this point over here is the activation energy without the catalyst. When you utilize a catalyst, this energy or this peak or the difference in these two energy levels will be much smaller. So the second curve you draw would have a lower peak. So this one over here is with the catalyst. And it has a much lower activation energy. When potassium chlorate is heated without a catalyst, potassium perchlorate and potassium chloride form. Explain why this reaction is described as a disproportionation reaction. Disproportionation is a reaction in which the same species is oxidized and reduced, which here will be the chlorine. Okay, in a potassium chlorate, you have the potassium ion with a charge of +1 and the chlorate ion with a charge of -1. To find the charge of chloride, to find the charge on chlorine, here you will sum up the charges of all the elements in the ion and equate that to the total ion, to the total charge. Since the charge on chlorine is unknown, I'll denote that by X. And oxygen always has a charge of -2, and you have 3 of those in here, and the total charge is equal to -1. So the charge on chlorine here is equal to 6 minus 1, which is +5 over here. And as for potassium perchlorate, again potassium has a charge of +1, perchlorate ion has a charge of -1. You have 4 of oxygen atoms here, and the total charge is -1. So here the charge is equal to +7 on chlorine. So you go from +5 to +7. This is oxidation or loss of electrons. Okay, this +7 should be on this chlorine atom over here, right? So this is oxidation. However, in potassium chloride, chlorine has a charge of -1, which is reduction, gain of 6 electrons from +5 to -1. As you can see, the same species is not just oxidized but also reduced, which is why this reaction is called disproportionation reaction. Molten potassium chlorate reacts with glucose. It melts at 630 Kelvin. At this temperature, both carbon dioxide and water are gases. Use the ideal gas equation to calculate the volume in meter cube of 1 mole of gas at 630 Kelvin and 1 times 10 to the power 5 pascals. Show your working. So this is a simple question of 1 mark. You have the ideal gas equation and you're supposed to find the volume, which is equal to the number of moles, and that's 1 mole multiplied by the gas constant and the temperature in Kelvin divided by the pressure, which is 1 times 10 to the power 5. And this is equal to 0.0524 meter cube. 5 grams of glucose reacts completely with molten potassium chlorate. Use your answer in D part 1 to calculate the total volume of gas released at 630 Kelvin and the pressure stated here, and they've also given you a substitute value to be used in this question if you couldn't answer the previous part. So the previous part tells you that each mole of gas has a particular volume, which means if you can find the number of moles of gas produced in this reaction, you can use that to find the number of or the volume of gas produced in this reaction as well. So the first part of your answer will include finding the total number of moles of gas produced in this reaction, which are carbon dioxide and water vapor. And you start with 5 grams of glucose, which will react completely. You will convert this 5 grams of mass into the number of moles. Then you will use the ratio in the equation, which states that 1 mole of glucose produces 6 moles of carbon dioxide and 6 moles of water, as in 1 mole of glucose will provide you with a total of 12 moles of gases. You use this 5 grams to find the number of moles of glucose, and then use the number of moles of glucose to then find the total number of moles of gases, and then you will use that as well as the ratio of moles to volume of gases we found earlier to get to the final answer. Right, so 5 number of moles is equal to mass divided by molar mass or molecular mass in this case. So the molecular mass of glucose would be 6 times 12 plus 6 times 16, which is 180. So number of moles of glucose is equal to 0.0778 moles. Given that each mole of glucose gives you 12 moles of gases, 12 moles of gas, which is 6 moles of carbon dioxide and 6 moles of water. That means you will multiply this moles value of glucose by 12 to find the number of moles of the gas produced in the product, which is equal to 0.333 moles. And according to the previous answer, 1 mole of gas has a volume of 0.524 meter cube. So you multiply 0.333 by the volume of 1 mole of gas to get to your final answer, which would be 0.0175 meter cube. E. The structure of glucose is shown in figure 3.2, part 1. Complete table 3.1 to identify the number of primary, secondary and tertiary alcohol groups present in the structure shown in figure 3.2. Okay, so primary alcohol has 1 alkyl group and 2 hydrogen atoms on a carbon atom. So this over here is an example of a primary alcohol. You have an alkyl group, 2 hydrogen atoms on the carbon that's bonded to the hydroxyl group. In secondary hydrogen, the carbon that's bonded to hydroxyl group will be bonded to 2 alkyl groups and 1 hydrogen atom. So this is primary, tertiary, and for the primary, secondary, and for the tertiary alkyl group, the carbon that's bonded to a hydroxyl group will be bonded to 3 alkyl groups. So let's start with this one over here. The carbon atom in this case is bonded to a hydroxyl group, an alkyl group, and 2 hydrogen atoms. So this is a primary alcohol. Okay, that's 1 for primary. Okay, then let me just erase this. Here you have 2 alkyl groups and 1 hydrogen atom. This is a secondary alcohol. So 1 for secondary. And the same goes for this carbon atom over here as well as this carbon atom over here. Both of them are bonded to 2 alkyl groups and a hydrogen atom other than the hydroxyl group. So that's another 2 secondary alcohols. And then this carbon atom over here, okay, this is also secondary alcohol. So you have 2 secondary alcohol groups, 1 primary alcohol group, and no tertiary. Two separate samples of aqueous glucose are tested with the reagents shown in table 3.2. Complete table with the observation of each reaction, and you can write no reaction if that's applicable. So you start with aqueous acidified potassium manganate, which is warm. This is an oxidizing agent. So glucose has primary and secondary alcohol groups as well as an aldehyde group over here. Warm acidified potassium manganate is a strong oxidizing agent which oxidizes the aldehyde part to carboxylic acid. And for the observation, you would observe that the purple color due to potassium manganate turns colorless. And Felling's reagent, when it's warmed, also reacts with aldehyde group, and you would observe the formation of a red precipitate. As for aqueous alkaline warm iodine, this is the reagent used in iodoform reaction. So in an iodoform reaction, you can have a positive result, which is formation of a yellow precipitate. Now this can happen when you have either of these structures, which I'll draw over here. When you have a carbon that's bonded to hydroxyl group, and a terminal methyl group, or if you have a carbon that's bonded to, let's say, carbonyl carbon, which is also bonded to a terminal methyl group. If the reagent, in case of having either of these two groups in an iodoform reaction, the product would be a yellow precipitate. However, in glucose, you don't have either of these. As you can see, neither the aldehyde nor the hydroxyl groups are bonded to a carbon atom that's also bonded to a terminal methyl group, which means here you will get a negative result, which you'll observe nothing, you'll observe no visible reaction in this case. Part 3, there are many structural isomers of glucose. Define structural isomerism. This is involved in molecules that have the same molecular formula but different structural formula, which can result from position or functional group. For example, let's take the example of propanol. In propanol, you have 3 carbon atoms, so the hydroxyl group can be found on the first carbon atom or on the second carbon atom. This is structural isomerism due to position. The other possibility is structural isomerism due to branch. So let's take the example of pentane, which has 5 carbon atoms, right? You could have this structure or another structure which has 4 carbon atoms in the backbone and then a methyl branch. Both of these molecules have the same molecular formula, as in they have the same number of carbon and hydrogen atoms. However, in pentane is a straight chain molecule and 2-methyl butane is a branched molecule, so they are structural isomers. Similarly, propane 1-ol and propane 2-ol have the same number of carbon, hydrogen and oxygen atoms, but they are structural isomers due to the fact that they have different positions of the hydroxyl group. Question 4. Compounds C and D are alkenes with the same molecular formula C5H10. Okay, so this is another example. They are structural isomers due to the difference in position of carbon-carbon double bond. In molecule D, the carbon-carbon double bond is between first and second carbon atoms. In molecule C, it's between the second and third carbon atoms. A part 1. Give the systematic name of D. So you start by looking at the number of carbon atoms in the backbone chain, which is 1, 2, 3 and 4 carbon atoms, and the functional group is an alkene. So this is butene or but1ene. In addition, you also have a branch on the third carbon atoms. So this would be 3-methyl but1ene. As for C, you have the carbon-carbon double bond between second and third carbon atoms. So this would be 3-methyl but2ene. Part 2. Explain why C and D do not show geometrical or cis-trans isomerism. Okay, so isomerism has 2 main types: structural and stereoisomerism. We discussed structural isomers in the previous part, which it can be due to position of functional group or due to branch. Right. Stereoisomerism is also divided into 2 types. One of them is due to optical isomers, which we'll see further in this question, and the other one is cis-trans or geometric isomerism. So cis-trans isomerism occurs when you have a carbon-carbon double bond in a compound and both of the carbon atoms are bonded to 2 different atoms or groups of atoms. So let's say if you were to have 2 same kinds of atoms on any of the 2 carbon atoms, if you had, let's say, cyanide and CH3 over here, even though the second carbon atom here has 2 different groups of atoms bonded to it, the fact that the first carbon atom involved in the carbon-carbon double bond is bonded to the 2 same atoms means that it cannot form a cis-trans isomer. However, let's take the same example, except now in this case you have another methyl group on this carbon atom, right? So each of the 2 carbon atoms that are now involved in the double bond are bonded to 2 different groups of atoms. This is hydrogen versus methyl, cyanide versus methyl. Both of the groups of atoms that are bonded to the carbon-carbon double bond, that are bonded to the atoms involved in alkene bond, are different. So this would form a cis-trans isomer. And now they're asking why C and D do not show cis-trans isomerism. So let's expand the structure of C and D. This is C. So you have CH3, CH, CH3 again, and this carbon atom is double bonded to a carbon atom that's bonded to CH3 and then a hydrogen atom. Okay, you don't need this hydrogen atom over here. Now as you can see, This carbon atom is bonded to 2 methyl groups, which means it cannot form a cis trans isomer. Let's look at D. This is D. So you have carbon, it's bonded to 2 methyl groups, a hydrogen atom, and then this is bonded to a carbon that's double bonded to a terminal carbon. It has to be bonded to 2 hydrogen atoms. This one over here is bonded to a single hydrogen. So these are the 2 carbon atoms involved in the double bond. This carbon atom, okay, this one's bonded to a hydrogen and an alkyl group. However, the second carbon atom is bonded to the 2 same atoms, so it can also not form cis trans isomers. Part 3. Draw the structure of a molecule that's a positional isomer of C and D. A positional isomer means that this isomer must have the same branch. However, you can change the position of the branch or the position or the position of the alkene bond, the carbon-carbon double bond. What this means is the branch can it must remain on the second and third carbon atom, because if you were to put it on the first or the last carbon atom, it would no longer remain a branch, so you would have a branched isomer. But you only want to look at a positional isomer, not a branch isomer. So you can change the position of the branch between these 2 carbon atoms or the position of the alkene double bond. So when you look at C, it can't really be modified by changing the position of either the branch or the double bond. If you change the position of the double bond, it would result in D, and so you need to look at something else. If you change the position of the branch, it would remain the same molecule. Now for D, if you change the position of the double bond from first and second carbon atom to the second and third carbon atom, it would turn into C. However, if you change the position of this branch and put it on the second carbon atom, you would end up with a structural isomer with difference in the position. So you have a positional isomer here, which is 2-methyl but1-ene. So that's CH3, CH2, and then you have a carbon that has a methyl branch, and it's also double bonded to CH2. Part 4. Give the structural formula of the compound formed when D reacts with hydrogen in the presence of platinum catalyst. So the reaction of an alkene with hydrogen is reduction reaction, which will reduce this alkene group to an alkane group. So now the double bond will break and you will end up with an alkane. With this structure, and this is 3-methyl butane. So you have CH3 and then a carbon that's bonded to a hydrogen as well as a methyl branch, and then you have CH2, CH3. Okay, I realize another way you could write this name should be CH3 twice because you have two methyl groups on the same carbon atom, followed by CH, CH2 and CH3. This one is not in the mark scheme, so I'm not sure why that is. So it's safer to write this one over here. Part 5, C can form an addition polymer. Draw the structure of one repeat unit of this addition polymer. Okay. This is C over here. When it forms an addition polymer, the carbon-carbon double bond breaks down to form new single bonds adjacent to these carbon atoms. So you will go to form a addition polymer repeat unit. So now you have a single bond between the two carbon atoms, and then the remaining of the structure from the monomer, and then you have two open bonds to allow the formation of a polymer. B, the mass spectrum of C shows a molecular ion peak at 70. This peak has a relative intensity or height of 48.7. The relative intensity of M+1 peak is 2.7. Show that this information is consistent with the molecular formula of C. Okay, C has a molecular formula C5H10. Here's the structure of C. Right. The molecular ion peak, or the peak at 70, occurs due to the fragment or the entire molecule which has an MR of 70 due to 5 carbon atoms and 10 hydrogen atoms. And then the M+1 peak occurs due to molecules of C that have carbon-13 isotopes. And you can see the difference in their height or intensity. The M peak, which occurs due to carbon-12 isotope, has a peak of 48.7. The M+1 peak, due to carbon-13 isotope, has a height or intensity of 2.7. As to how to answer this question to show that it's consistent with the molecular formula, well, you can use the ratio of M to M+1 peak heights or their intensity to find the number of carbon atoms in a compound. Given that in a sample of any carbon atoms, the ratio of carbon-12 to carbon-13 isotopes is 99 to 1. So let's say you had 100 carbon atoms, 99 of them would be carbon-12 isotopes and one of them would be carbon-13 isotope. So carbon-13 makes up 1.1% of all carbon atoms. So in simple words, the ratio of M to M+1 peak is equal to 100 to 1.1 N. So this is the ratio of their heights or their intensity. So 100 is to 1.1 N is equal to 48.7 is to 2.7. So 100 over 1.1 N is equal to 48.7 divided by 2.7, which means 48.7 into 1.1 N is equal to 270, and the number of carbon atoms here is equal to 5. So you have 5 carbon atoms in molecule C, and when you find the molecular mass of this compound, it turns out to 70, which was the mass which is where you have the molecular ion peak for compound C, and this is how it shows consistency with the information given. Part C. C and D both react with hydrogen bromide. C reacts with it to form E. Complete the diagram in figure 4.2 to show the mechanism for this reaction. Draw the structure of the organic intermediate. Include all the charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Now this is an electrophilic addition reaction in which bromide acts as the electrophile, and the carbon-carbon double bond will break down to form carbon-carbon single bond, as well as the addition of the electrophile. You start with hydrogen bromide, which is a polar molecule, which means hydrogen will have a positive dipole and bromine will have a negative dipole. This occurs due to the difference in electronegativity between hydrogen and bromine. Hydrogen is less electronegative than bromine, so bromine will attract the bonding pair of electrons in the hydrogen-bromine bond towards itself, which results in the negative dipole. Now, the positive dipole on the hydrogen is attracted by the electron density of the carbon-carbon double bond, so it will receive a pair of electrons from the carbon-carbon double bonds. Okay, let me erase the part which is not part of the answer. You will need to only represent the dipoles as well as the curly arrow. Hydrogen will gain an electron from the carbon-carbon double bond, and then the hydrogen-bromine bond will break by heterolytic bond fission. So both of the electrons that were involved in this bond will be received by bromine. So bromine had one electron of its own and one electron from hydrogen in this bond. So now bromine will gain an extra electron, which will result in bromine gaining a negative charge. This is how you will represent bromine, with one extra electron and a negative charge. Now, as you can see in the product, the bromine bonds to the second carbon atom, which means hydrogen must bond to the third carbon atom in molecule C, right? So when the double bond breaks down and a hydrogen receives an electron from this double bond, the other carbon atom which was involved in the carbon double bond will lose an electron, and so it will gain a positive charge. This is the carbocation because it has a positive charge, and then the bromine with the negative charge will contribute an electron to this carbocation and bond with the carbon that has a positive charge to form the final product. Part 2, D reacts with hydrogen bromide to produce F, a chiral bromoalkane. Draw the structure of F. Right, so you have D and it reacts with hydrogen bromide to form, it can form two different products. In the first product, the bromine can bond to the first carbon atom. In the second product, the bromine can bond to the second carbon atom. Now you need to select which one of them has a chiral center, which forms the chiral bromoalkane. This carbon atom is, okay, let me use a black color. This carbon atom is not chiral because it's bonded to two CH3 groups. Okay, what's a chiral carbon? It's a carbon atom that's single bonded to 4 different atoms or groups of atoms. This can be a hydrogen atom as well. So here this carbon atom is bonded to 2 methyl groups, which makes it not chiral. This carbon atom is bonded to 2 hydrogen groups, again not chiral. This carbon atom is also bonded to 2 hydrogen atoms, which means this molecule is not the chiral bromoalkane. Again, this carbon is not the chiral carbon. This carbon on the other hand is bonded to a methyl group, a bromine atom, a hydrogen atom, and an alkyl group, which is different from the first alkyl group. So this is the chiral bromoalkane, and so you will draw that product in for your answer. Part 3, explain why the reaction of hydrogen bromide with C and D produces different major products. Major products are the products that are formed from the more stable carbocation. As we saw earlier in the previous part, When hydrogen bromide reacts with C or D, it can form two different products depending on which carbon atom from the double bond the bromine atom bonds to. Okay, and this will involve different carbocations as the intermediate. When you look at C and it reacts with hydrogen bromide, the bromine can bond to the second or the third carbon atom, which means it can form two different carbocations for the intermediate. If the bromine atom bonds to the second carbon atom, it will form this intermediate, which is a tertiary carbocation, as the carbon that has a positive charge is bonded to three alkyl groups, two methyl groups, and then this one over here. On the other hand, if the bromine were to bond to the third carbon atom from C, then you'll have the positive charge on the third carbon atom. Right, this is a secondary carbocation because the carbon that has the positive charge is bonded to two alkyl groups. So here you have the secondary carbocation and the tertiary carbocation, which can be intermediates in the reaction of C with hydrogen bromide. Now let's look at D. When D reacts with hydrogen bromide, the bromine can bond to the first carbon atom or the second carbon atom. If bromine were to bond to the first carbon atom, you would end up with this carbocation that has a positive charge on the first carbon atom, and since this carbon atom is only bonded to one alkyl group, this makes it a primary carbocation. If the bromine were to bond to the second carbon atom from D, that means the second carbon atom would have a positive charge, and since this carbon is bonded to two alkyl groups, that makes it a secondary carbocation. Depending on which carbocation you have as the intermediate, you will get different products, and the more stable carbocation produces the major product, whereas the less stable carbocation produces minor product. And the stability of carbocations increases in the order from primary to secondary to tertiary. Tertiary carbocations being the most stable. So major products are formed from either primary or secondary carbocation, and minor products can be formed using either of primary and secondary. Right, and the reason that a tertiary carbocation forms major product is because tertiary carbocation is more stable due to the positive inductive effect of alkyl groups. So alkyl groups are electron donating. What that means is when you form a carbocation, the alkyl groups will push electrons towards the carbon that has a positive charge. This will reduce the positive charge on the carbon atom, and this will make the carbocation more stable as compared to a primary carbocation, where the carbon with the positive charge is bonded to only a single alkyl group. This has a lower positive inductive effect, which makes a primary carbocation less stable than a tertiary carbocation. So, to answer this question, both C and D can form different carbocations, which is why they will have different stabilities of carbocations, and they form different major products. The major product in case of C will be formed using this tertiary carbocation over here, and major product in case of D will be formed using secondary carbocation, which is more stable than the primary carbocation. Part D, C can be used to form H. One possible synthesis of H is shown in figure 4.5. Different portions of C are used in the reactions 1 and 3. Some of the products are then combined to produce H. Figure 4.5 does not show any of the inorganic products of the reaction. Okay, in the first reaction, hydrogen bromide reacts with C to produce bromoalkane, and then it undergoes reaction 2 to produce J. In reaction 3, you have two products. One of them is a ketone, and when a ketone is formed using an alkene as a reactant, this is a strong oxidation reaction in which the carbon-carbon double bond breaks down, and the ketone is formed using this part where the carbon atom involved in the double bond is bonded to two methyl groups, which results in pentanone. And then this part of the alkene, where you have a carbon atom that's bonded to an alkyl group and a hydrogen atom, will be converted to carboxylic acid. In this case, it will be ethanoic acid, since you have two carbon atoms. So G is ethanoic acid. And for this reaction, you will need hot concentrated acidified potassium manganate. Right. Now you have G, which is an acid, reacting with J to form an ester, which means J has to be an alcohol. Okay, so this part is coming from this part comes from G, which is the acid, and the remaining portion comes from the alcohol J. So alcohol J must have the structure over here. This must be J. And according to reaction 2, J is made using E. And when you go from a bromoalkane to an alcohol, you would need to use aqueous sodium hydroxide as the reagent, and this is called nucleophilic substitution reaction, as hydroxide ions will substitute bromide ions. Right. So now we have all the reactants and the reagents. And you're supposed to complete table 4.1 with the reagents and conditions for each of the reactions. In reaction 2, you go from E to J, which was bromoalkane to an alcohol. You would need aqueous sodium hydroxide. In reaction 3, you go from C to G and a ketone. So reaction 3 will use hot concentrated acidified potassium manganate. As for reaction 4, this is the reaction between an alcohol and an acid to produce an ester. It will be catalyzed by concentrated sulfuric acid. Hot concentrated sulfuric acid. And this is it. We are done with this paper. Thank you for watching.